Welcome everyone. Thank you for coming to the One World Combinatorics Onwards seminar. Our speaker today is Paulina Cecchi Bernales from Santiago in Chile. And she's going to speak to us about the interplay between combinatorics and dynamical properties in minimal symbolic systems.
Okay, thank you very much, Nadal, for the introduction. And thank you to Manon Cipulanti, who invited me to this seminar. I don't know if she's here. I suppose she's here. So the idea is of this presentation is essentially to talk to you a little bit about some examples of how we use combinatorial properties in infinite sequences to approach the study of some dynamical properties of the associated subshifts or minimal or symbolic systems. So I don't know if you are very familiar with the notions of the dynamic systems. So I have prepared a few slides, introductory slides about dynamical systems. Okay. So anyway, feel free to interrupt me anytime if you have a question. Okay. Okay. Oh no, but I haven't put the process. Sorry. Well, I think it's not that bad. Okay. So for us, a topological dynamical system is just a pair xt, sorry, where X is a compact metric space and C is the homomorphism acting on X. So the idea of dynamical system is just to study the evolution, the asymptotic evolution of the properties of the space X under the action of the homomorphism T, right? And we said that the system is minimal if it does not admit any proper subsystem, which means that for any invariant subset F, which is also closed, either F is the whole space X or is the empty set, right? In an equivalent way, when the system is minimal if any orbit, which is this set here, orbit of any point under the action of the map T, is a dense subset. Okay. I suppose you can see my pointer here. Okay. And in the symbolic world, we consider subshifts, which are a very special kind of dynamical system. So we consider a finite alphabet of just a finite set, which we call an alphabet A of symbols. And if X is any okay, so we can consider as subsets of the infinite sequences on the symbol A, and we endow A to the Z with the product topology of the discrete topology on each copy of A. So this defines a topological space, which is a Cantor space, if we have at least two letters. And in that space, we consider the shift transformation, which consists of shift any infinite sequence one position to the left. Okay, so S of any sequence is just to move one position to the left the sequence. Okay, and we always consider here the invertible systems. That's why we consider the two-sided infinite sequences, and so that this shift is a homomorphism on the space A to the C. And if X is any subset of A to the Z, which is closed and shift invariant, then X, S defines a topological dynamical system that we will call a subshift or a the associated languages. So for an infinite sequence with symbols in A, the language of the sequence X is just the set of all finite words, also called factors, appearing in the sequence X. And for a subshift, for a sequence, for a set of sequences, we said that the language of the subshift is just the union of the languages of all the elements of it. Okay. And somehow languages and subshifts are exactly the same because to any sequence one can associate a language, of course, but the other way around, if we take a sequence X bar, for instance, we can define the subshift associated to this sequence in this way. Oh, sorry, who is described here. All the other sequences whose language is contained in the language of X bar, okay? And that defines a subshift, okay? So we can also, for instance, define subshift, two-sided subshift, starting from one-sided sequences, okay? For instance, this, our favorite sequences, one-sided sequence, the Fibonacci word. We can take the one-sided sequence and then define the two-sided associated subshift as the set of all sequences whose language is included in the language of the Fibonacci word, okay? So we can also start with one-sided sequences, but then we turn, so that we can get homomorphisms, we turn to the two-sided word, okay? All right. And most of the time we consider minimal systems. So I already said to you that minimal systems are those for which all orbits are dense. So what does this mean in the symbolic framework? Well, for a factor W in the language of the subshift, we denote its length by this notation with bars. So in the minimal case, since all shift orbits are dense, one has that on one hand, any word appears in any sequence of the system. So all sequences share the same language. So one can study the language of the general system by studying the language of any particular sequence. And this is also equivalent to the fact that every sequence is uniformly recurrent. Okay, so this means that any factor V of the sequence X appears infinitely often in X, but also with bounded gaps. Okay, so for any. Okay, so sorry, this is not well written because this n may depend on d. Okay, so for all x and for all factor of x, there is an n such that. No, sorry, this n depends on w. So there is an n that depends on w, such that if other factor sufficiently large that contains also the word w. Okay. So this implies that in minimal subshift, all language are the same, and also all sequences are uniformly recurrent, meaning that every factor appears with bounded gaps, infinitely often with bounded gaps. Okay. So uniform recurrence is the combinatorial analog of minimality in symbolic systems. Okay. Just for notation, we will denote Ln of x, the set of words of length n in the language of the subshift. And well, a very important example for us will be a substitutive subshift. I imagine that you know very well substitution. So let me just introduce some language and notation. For us, a substitution is just a morphism from the free monoid of finite words on A to itself, which is non-erasing, meaning that the image of any letter is not the empty word and letter on too, meaning that every letter here in A appears in the image of something. And if the length of the iterase sigma to the n of A for any letter increase and diverges to infinity as n goes to infinity, we will say that the substitution is everywhere grown. Okay, so this means that we can produce infinite sequences by iterating the substitution. So for instance, again, our favorite example, the Fibonacci substitution, it is defined like that. So A goes to AB and B goes to A, and then we extend by concatenation. This produces infinite sequences like the Fibonacci one. So given a substitution, one can define the substitutive subshift associated, which consists of all the sequences, all of whose factors, this symbol here means factor, W is a factor of X, all whose factors are also factors of some sigma to the n of A for some n and some A, okay? And this is equivalent to define the system by taking an infinite word obtained by iterating the substitution and then to define the associated subshift using the language, okay? This is equivalent. So substitutions, non-erasing later on to everywhere grown substitution, produce symbolic systems. Okay, and this system will be minimal when the substitution is primitive, meaning that there exists a positive integer n such that any letter appears in sigma to the n of any other letter. Okay, so for all A, B letters, A appears in the image of the n iterated sigma of B. Okay, so in this case, one can see that every sequence is uniformly recurrent, and then the system, the associated symbolic system, is many. All right. So the general question here for us is how these combinatorial properties, some combinatorial properties of sequences, interact with dynamical properties of the associated symbolic system. So we already seen that minimality is equivalent to the fact that every sequence is uniformly recurrent. So let me now say a few words about invariant measures, okay? Because if we have a topological dynamical system, XT, we always want to study how are the invariant measures associated to these systems, okay? So a Borel probability measure mu on X is called invariant, it's called an invariant measure if it is preserved under the action of T. Okay, so for any Borel subset A, this is the Borel sigma algebra. So for any Borel subset A, the measure of the image under T of A is the same as the measure of A. Okay, and we said that an invariant measure is ergodic if whenever A is an invariant set, is exactly an invariant set, meaning that the pre-image of A is equal to A, then necessarily either the measure of A is null or 1, okay? And that means that the associated measurable system cannot be decomposed in smaller pieces, okay? Okay, so the set MXT will be the set of all invariant measures admitted by a dynamical system XT. And this is a very interesting object that somehow reflects how many measurable dynamical systems are housed by this topological dynamical system. Okay, it is always non-empty. This is the Krylov-Bogoliubov theorem. Okay, so topological dynamical system always admits at least one invariant measure. And if it admits only one invariant measure, then the system will be called uniquely ergodic. Okay. So first question is, what is the combinatorial property which reflects unique ergodicity in symbolic systems? Okay. And the answer is frequencies. Okay. So the frequency, if you have an infinite sequence on a symbolic system X, and you consider a factor W of X, and this notation here, so bars, and the portion of xk up to xl. So this notation here, bars xk xl sub w, denote the number of times that the word w appears in this portion of x. Okay. So the frequency of w in x is this limit when it exists. This means that this quantity here is the relative proportion of w's in the central portion of x. So this is the frequency is the asymptotic relative proportion of w in the sequence x, okay, when it exists. But it always exists, thanks to the ergodic theorem, at least mu almost everywhere for any ergodic measure mu. Okay, so for any ergodic measure mu, this limit always exists and equals this quantity here, the measure of the cylinder W. Okay, so this brackets means cylinder. The cylinder W is the set of all sequences of X starting by the word W. So the frequency of W on X equals the measure of the cylinder W for mu almost every X in X and for any ergodic measure. Okay. But being uniquely ergodic is stronger than that. What we know is that the subshift is uniquely ergodic if and only if every factor has uniform frequencies. Okay, so uniform means that this limit here, because here we have the relative proportion of W in the central portion of X, but we can consider the relative proportion of W in any place of X. So if this limit, it always exists and is independent of the place in X we are looking to, then the frequency is uniform. Okay, so what we know is that this is equivalent to the fact that the associated symbolic system is uniquely ergodic. Okay, the system will admit only one invariant measure. Sorry, if and only if every factor has uniform frequency, and in that case, for all X in X, the frequency of W in X is exactly the unique measure of the cylinder W. All right, so this is another example of how combinatorial behavior interacts with dynamical, right? And last example has to know how to do with a factor complexity. Okay, because beyond the uniquely ergodic case, one can have several ergodic measures. Okay, so the set MXT is a convex space whose extreme points correspond to this ergodic measure. Okay, so the question here is how many ergodic measures supports any a given dynamical system. Okay, and there is a very beautiful result by Boucher-Nixon, which says that factor complexity restricts the number of ergodic measures that a given minimal subshift can admit. Okay, so I recall you that the factor complexity of the subshift is just the factor complexity function, I should say, is the function that counts the number of factors of any given length. Okay, so px of n is just the cardinality of language of order n of x. And the theorem says that for a minimal subshift, if this quotient here goes in the sense of the limit to something finite, alpha, then the system admits at most the integer part of alpha, or 1 if alpha is less than 1, ergodic measure. Okay. So in particular, if this limit is finite, then the system, admits at most finitely many ergodic measures. Okay, So any sublinear behavior of the factor complexity function implies necessarily that the system admits only finitely linear coordination. This is a very, very interesting result. Okay. And also illustrate how this very combinatorial notion, which is a factor complexity, restricts the dynamical behavior of the system. Okay. Okay. So now our work. So I forgot to say that this is a presentation covers a part of our work with Valérie Berthet and Bastien Espinosa. So now I'm going to speak you a little bit about what we have done in our work. The dynamical properties we are interested in are continuous eigenvalues of dynamical systems. So I will introduce what continuous eigenvalues are, and then how we can approach the study of continuous eigenvalues using combinatorial objects. Okay. Okay. So. Okay, so a complex number lambda is a continuous eigenvalue of the topological dynamical system xt if there exists an associated continuous eigenfunction that is a non-zero continuous function from x to the complex number such that f composed with t is lambda f, right? For simplicity reasons, we consider here additive eigenvalues. Okay, so the additive counterpart of this alpha in R is a continuous eigenvalue, an additive continuous eigenvalue of the system. If there exists a non-zero function f from x to the from R mod z, such that now f composed with t is f plus alpha mod z. Okay. And we denote ext, the set of additive eigenvalues of the system xt. This is an additive subgroup of the real numbers. Okay, and it is preserved under conjugacy of dynamical system and also under topological factors. So it is an interesting object to study. So we will be interested in two things mainly. On one side, to decide specifically when given lambda or alpha is an eigenvalue of a given system. And we will be also interested in to estimate the rank of ext, which is the size, the Q dimension of the Q vector space generated by the additive eigenvalues, okay? As a subset of R. Okay. Okay. And the combinatorial objects that we use to approach this study are coboundaries, okay? So let me define what coboundaries are. When you have a minimal subshift, you can consider what we call return words. This is a concept introduced by Fabian Johan, if I'm not mistaken. So a word in the language of X is called a return word to the letter A in the alphabet if three conditions hold. So W start with A. W can be followed by A in the language, and also there are no other appearances of A in the middle, right? Okay, so it's a W represents a way to first return to A in the language, okay? And what is a letter coboundary? A letter coboundary of this system is just a morphism from the primonoid A star to R mod Z, such that for every return word, C of W is 0. Okay, so these are morphisms from A star to R mod Z, which vanishes in return words. And we say that a letter co-boundary is trivial if it's always zero. This is, of course, is a co-boundary. But we can also construct non-trivial co-boundaries. For instance, here, this is just an example of a co-boundary. Okay, so consider the substitution sigma on the alphabet A, B, C described here. Here I put the letter H, not to be confused with the letter C. Okay, but the co-boundary is H. So define H of A1, H of B minus 1, H of E0. This map, and then concatenate by sums, okay? Extend by concatenations, which are sums in this case. So this defines a non-trivial co-boundary, right? So for instance, if you apply sigma to A and then to sigma square of A is ABA CBABA, right? So you can see that BAC is a return word to the letter B. And if you apply H to BAC, you obtain -1 plus 1 plus 0, which is 0. Okay, this is just an example, but you can check that this defines a non-trivial boundary of the symbolic system associated to this substitution. This notion was introduced by Bernard Host, who characterized continuous unmeasurable eigenvalues of substitutive systems by using the notion of co-boundaries. Okay, so here the theorem for a primitive substitution which is injected on the letters and also recognizable. Okay, so recognizability is explained here, but don't read it yet. So the characterization says lambda in the complex number lambda is an eigenvalue of the substitutive system if and only if there exists a positive integer p such that for all letter A, this limit here, which he called h of A, exists and defines a letter co-boundary, meaning that the map sending each letter A to h of A is a co-boundary in the sense of the previous definition. Okay. So recognizability means basically that one can desubstitute sequences in the substitutive system. Okay, in elementary parts of the form sigma to the k of A. It's a strong form of injectivity or desubstituability. I don't know how to say it in English. But well, it is a usual assumption on substitutions. Okay, so looking at this result, one sees that it would be interesting to know when co-boundaries can only be trivial. Okay, but this would because this would simplify this criterion to decide whether lambda is an eigenvalue or not. Okay. And that problem we approach using the object of extension graphs. Okay. So what is an extension graph? When you have a subshift S on the alphabet A, one can consider two copies of the alphabet. So a left copy AL and a right copy AR, with the canonical bijection which send to each letter to the left copy and the right copy. Okay, and we will construct a bipartite graph using these two disjoint copies of the alphabet as follows. So define the sets for a factor of the language W. Define the sets EL, which are all the possible left extensions of W, letters which can precede the letter W in the language, and right extensions. Okay, so letter which can follow the word in the language. And construct the extension graph of W using as vertices this disjoint union, EL union ER, and we put the edge between two vertices, if and only if an edge ALBR, if and only if the word W connects the letter A in the left and the letter B in the right. So if AWB belongs to the language. Okay. So just for give you an example, the same substitution I wrote before, sigma. In this case, we can observe that the two symbol words, two letter words of the language will be 0110 to 102. Okay. So how does the extension graph of the empty word look like? That way. Okay. So here the left copy, the right copy of the vertices, and then the edges connecting 10. Okay, 1001 to 102. 1001 to 102. Okay. This is the extension graph of the empty word. And a connected component in the graph is just a subset which is maximal in the sense of the inclusion, such that every pair of points in that component is connected by a path, some path in the okay. So our idea is to relate co-boundaries to these extension graphs. Okay. So let's denote the set of all letter co-boundaries of the system, and let R denote the number of connected components in the extension graph of the empty word. This set Cx has a natural vector space structure using pointwise sum of functions and scalar multiplication. So what we have is the following. For a transitive subshift, transitive is a little less than minimal, meaning that at least one orbit is dense. So if you have a transitive subshift, as an R vector space, the set of co-boundaries Cx has dimension R minus 1. Okay, so in particular, this extension graph is connected if and only if every co-boundary of the system is trivial. So that allows us to provide sufficient conditions to having only trivial co-boundaries, which is interesting in view of, for instance, of the Host theorem of the characterization of continuous eigenvalue. But we can also provide sufficient conditions to having trivial co-boundaries using, of course, this result, but another quantities, for instance, again, frequencies, okay? So for instance, if you consider a subshift, a minima subshift, you can, for all n and any invariant measure mu, you can define this quantity here. So consider this set here is the Q vector space generated by all the frequencies of, measure of cylinders of letters W of length n. And then you take the Q dimension of this, and you call this dn mu, okay? So dn mu is the size of the Q vector space generated by all the measures of cylinders of words of length n. And then denote for this n, Kn denote the set of all connected components in all the extension graph of all words of length n, okay? So for each word, you have an extension graph, and then you consider the union of all the connected components of all words, okay? So our lemma says that for a transitive subshift, this quantity d mu n is bounded from above by the factor complexity of n, the number of connected components of graphs of extension graphs of words of length n minus 1 plus 1, okay? Okay, so I think I should be a little bit quicker. Okay. So with that lemma, we can provide sufficient conditions for having trivial copolyps. Okay, because here is a sufficient condition. So for a minimum such that there exists at least one measure, one invariant measure for which the vector of letter frequencies, measures of letter cylinders, has rationally independent coordinates, then any coboundary of X is trivial. And this follows directly from the previous lemma because d mu1 in the case of rationally independent frequencies equals A, then the size of the alphabet, and then factor complexity of size 1 is just the alphabet, the size of the alphabet. Kn minus 1 is the number of connected components of the extension graph of the empty word. So you get that this K0 is less than or equal than 1. So that must be 1. Okay, so the graph is connected. And then by the previous theorem, all coboundaries are trivial. All right. Okay, and the other thing is the size of this space EXS. Well, what we have is that the Q dimension of EXS is bounded by this limit. Also regarding factor complexity and number of connected components of extension graphs. This follows from this general fact, but I think I will skip here, but because it is a bit technical. But what is important is that in some cases, one can get a cleaner bound, which is here. Okay, so in some cases, for instance, for primitive unimodular substitutions, which are substitutions for which the incident matrix is unimodular, invertible under Z, we have this cleaner bound, which is that the dimension of the set of eigenvalues is bounded by the size of the alphabet minus the number of connected components of the extension graph of the empty word plus 1. Okay. So for some cases, we have a very nice bound on the size of the Q vector space generated by the eigenvalues. Okay. And another interesting property in combinatorial and also dynamical terms is balance. I imagine that you are familiar with this notion, so just let me introduce the notation. We say that an infinite word X is balanced on the factor W if there is this constant CW, positive constant CW, such that any two other words of the language of X, B and B prime, having the same length, the number of occurrences of W in B and B prime is bounded by this constant, okay? And we said that the system is balanced on factors if any sequence is balanced on any factor, and letter balance if any sequence is balanced on every letter, just letter, okay? So for instance, as you may know, Starman sequences are exactly the infinite binary aperiodic words, which are one letter balance, okay?
So sorry for interrupting you, but
yes.
The definition of the balanced subshift. So the balanced CW depends on small x. Is it right? Sorry. X is capital X is minimal. Sorry.
Yes, exactly.
It dependent on x, small x. Sorry.
Exactly. So it depends on the word W and on X, but if all sequences are balanced, we say that the system is valid.
Thank you.
Okay. So dynamical speaking, the interpretation of this is that these quantities here, so the difference between the ergodic averages and the frequency is this deviation is bounded, And in particular, balanced subshifts are uniquely ergodic. They admit only one invariant measure, but the convergence of the Birkhoff sums to the frequency is very fast. Okay, so it's a stronger property than unique ergodicity. Sorry. And also, if the system is balanced on the factor W, then the frequency, the measure of the cylinder, that should be W, sorry, the measure of the cylinder W will be an additive topological eigenvalue. Okay, so in that case, all frequencies define eigenvalues. Okay. So what we have is a characterization of balance using coboundary. Okay, so for the case of primitive substitutive systems. Okay, so when we have primitive aperiodic substitution, one can define using the incident matrix of the substitution this space V sigma, which is the stable space of the matrix, all the vectors which vanish under the right action of the matrix of the substitution. And we also have the coboundary space, which is the space of all vectors obtained from coboundaries of functions which are letter coboundary. Okay, and the characterization says that a primitive aperiodic substitution system will define a letter balance system if and only if the sum of these two subspaces has dimension codimension 1 in R today. That means dimension A minus 1. Okay, so the other dimension is captured by the frequency vector of frequency, and this has codimension 1. So this is an algebraic characterization of balance using this notion of coboundaries. Okay, and just for finish, because I think I'm running out of time, let me say a few words about minimal complexity. So there is this beautiful theorem by Tiedemann from 1999, which says that for a transitive subshift, the factor complexity of the subshift is bounded from below by this quantity here, so n minus 1, and t, which he called the irrationality degree of the system, which is the q dimension of the set of letter frequencies, which is the same as to say the maximal rationally independent frequencies, and the size of the alphabet, of course. So this is a generalization of the classical Morse-Hedlund bound on the complexity for binary sequences. And using our previous lemma on the inequality between d mu n and factor complexity and number of connected components of the extension graph, we can give a very, very short proof of this theorem. I put it here because it is really simple to understand. So I wanted to show you. So to prove this, note that T defines T equals, in our setting, equals d mu 1, okay? And this is, of course, less than or equal than d mu j for any j. And also, the number of connected components of words of length j minus 1 is at least the factor complexity in j minus 1, because each extension graph of any word of length j minus 1 produces at least one connected component. So using our previous lemma, we get that T is less than or equal than the factor complexity on j minus the factor complexity on j minus 1 plus 1. So if we sum up from j equal 2 to j equal n, one gets a telescopic sum, and this result here. Okay, and this is the same as to say that Px of n is greater than a minus 1, t minus 1 plus a, which is the Tiedemann result. Okay, so using our lemma, which in turn uses the notion of extension graphs, we are able to give a very short proof of this theory, right? And we also recover with this lemma and these tools a result by Melody Andreu and Julien Cassin from 22, but if I'm not mistaken, published just in 26, which says that if this minimal complexity here is attained and the frequencies are rationally independent, then the extension graphs of the systems are forced to be trees, okay? So connected and without cycles, okay? So if you take a transitive subshift and an invariant measure mu, if the minimal complexity of Tiedemann is attained and T equals A, meaning that every letter frequencies, the set of letter frequencies is rationally independent, then every extension graph is a tree, right? Of course, the converse is false because, for instance, codings of intervallic change are such that every extension graph is a tree, and they could have rationally dependent frequencies, okay? And these the subshifts in which every extension graph is a tree have a name. They are called dendric subshifts. So a subshift verifying that for all factor W, the extension graph of W is a tree are called dendric subshifts. They were introduced by Bertie and collaborators a decade ago, and they are kind of a generalization of a Stormian subshift in the sense of complexity. So, for instance, Arnold-Rossi subshifts and codings of interval exchange transformation and also Stormian subshifts are all dendric. And they have factor complexity size of the alphabet -1 plus times n plus 1, okay? So we have all these relations between being dendric, having Q-independent frequencies, and having minimal complexity, okay? So the second one is the theory of Andreu, Cassin, and us, okay? So Q-independent frequencies plus minimal complexity implies dendric. But also you can check thanks to this equality here for dendric subshift. It is not difficult to check these other two, okay? So if a subshift is dendric and has Q-independent frequencies, then it attains the minimal complexity, and also if the subshift is dendric and has a minimal complexity, then it's forced to have Q-independent frequencies, right? Okay, so just for finish, a quick recapitulation. What I had tried to do is to convince you that extension graphs and coboundaries are very interesting combinatorial objects, which allows us to approach the study of several interesting dynamical properties. They are closely related to factor complexity and frequencies. And from this relation between extension graphs, coboundaries, factor complexity, and frequencies, we are able to recover very relevant information to decide whether given lambda is or not a continuous eigenvalue of a primitive substituted system. We can also recover or estimate the size of the Q vector space generated by continuous eigenvalues. They allow us in some case, in the case of primitive substituted systems, to characterize letter balance. And they allow us to significantly simplify the proof of this very beautiful result of Tiedemann's on minimal complexity. And also they help us in providing sufficient conditions for being dendric. Dendric subshifts are also very interesting symbolic systems. So this illustrates somehow how these combinatorial objects allows us to approach very interesting dynamical properties. And I think that's all I wanted to say. Thank you very much.
Thank you very much, Paulina. We'll take some questions now. There was a question in the chat. Maybe I'll ask that one first. About so the question is, if a co-boundary takes values in R mod Z, why H in the example is not trivial? I guess that's the first introduction of co-boundary.
Okay. Yeah, but the co-boundary just takes values on R. Mod Z is just to stick to the original notation, which is the circle. So that's but you can consider the co-boundaries taking values on R. And if you want to take values on on R mod Z, you can take, instead of taking H1 minus 1, 0, you can take 1/2 minus 1/2 and 0. This is it.
Okay, are there any other questions? Hajime.
So thank you for nice talk. May I see page 21?
21.
Yes, it's a result on substitutive case. Is it possible to generalize this to sort of aesthetic version?
We don't know.
It's difficult.
Because we use, maybe in some cases, because we use all this Perron Frobenius machinery on the incidence matrix of the substitution, and this is not always possible to generalize this to a sequence of incidence matrices. But in some cases, with I would say yes, but not in full generality.
Okay. Thank you.
There's another question in the chat. Why is it called a co-boundary? Is there a notion of co-cycles here too? And are there higher co-boundaries, co-cycles?
What do you mean higher co-boundary?
I mean, like, well, are there co-cycles? Is this like a one co-boundary, like two co-boundaries, this sort of thing?
Okay, I don't know. I think they're called co-boundaries because they are characterized in terms of difference between. So when you see the extension graph, so you can see here the co-boundaries. So a co-boundary will always be the difference between something here in the right minus something here in the left for a connected pair of vertices. Okay, so I think this is kind of general terminology for co-boundaries. So difference between end minus start.
So that's kind of like a one co-boundary. Is there something like a co-cycle, that one co-cycle, like a crossed homomorphism or whatever it is in the...
I'm not sure.
Yeah. Okay, thank you.
Okay.
Are there any other questions? Yeah, Melody?
Maybe.
Can you hear me?
Yeah.
Yes.
Cool. Can we see the slide 24 or 25? Yes, that one. How do you prove the third point?
The third one?
Yes.
Because if you have, if you are dendritic, you always have this complexity here.
Yes. So you're already minimal complexity.
Exactly. And if you equal this to the minimum complexity, you get that T is forced to be the size of A. Right? So if you are dendritic and you attain minimal complexity, means that this quantity here equals the minimal complexity here of Tiedemann, right? So you made the computations and you get that T equals 8, size of 8. That means that that letter frequencies are rationally independent, right? Doesn't make sense?
Okay, I need to think about it.
Okay. But it's just make the computation. So you replace the complexity, this non-complexity for dendritic circuit, and then you say that if this is if this corresponds to the minimal attained complexity, then computations lead you to obtain that T must
Okay, I guess I misunderstood the statement of the. Okay, that's now I got it. It's what you meant by minimal complexity. I was not sure.
Yes,
okay.
This is a bit mysterious, but minimal complexity for me is to attain the Tiedemann's bound, right?
Okay, I will think about that. Thank you.
Okay, thank you, Melody.
Are there any questions? Any other questions? All right. If not,